Hello, my name is Vrany. I work at Labware, and on conferences like this I usually talk about debugging because I debug a lot and it's my favorite topic. But today I will talk about compiler. More specifically, I will talk about compiler we work on and about the individual components of the compiler and how, or try to explain what the components are, what they do, and give you an idea how you can use these components for your own project. Maybe all together, maybe each bit separately. So this is going to be the focus of this talk. But before we go any further, let me clarify what do I mean by compiler in the context of this talk. Because normally when small talkers are talking about compilers, they usually think of a staff, let's say, that takes a Smalltalk source code and produces a bytecode, which is then passed on to the VM to execute it. This is not the compiler I'm going to talk about. I'm going to talk about a compiler that takes some intermediate form of the code, not the original source code, but some intermediate form, bytecode, let's say, but not always a bytecode, and produces a machine code that is a code that runs on a real hardware. So this is going to be the focus of this talk, and this is the compiler I'm talking about. So as you may know, for a few years we've been working on a compiler for Smalltalk, or maybe not only Smalltalk, because the compiler itself it's a pretty general thing, but we are building it in Smalltalk, using the Smalltalk objects, Smalltalk models, and things like this. And during the course of building it, we built several components, which I think are interesting in itself. So this is what I'm going to talk about today. So the first component we call machine arithmetic. And this is the basic to work with bit vectors, bytes, extract bits from individual parts of the bit vector, shift them, do this kind of basic things. So that was the initial idea for machine arithmetic, but then it grew into quite a large piece. But we will get into it soon. The second bit I'm going to talk about is an ArchC. That's our library or component, if you will, to work with different ISAs, different architectures, like MIPS, Power, x86, ARM, and work with instructions, encode the instructions, decode, that kind of thing. And finally, there is a Tinyrossa, which is a compiler that is built on both the RC and machine arithmetic, and that's the actual thing that compiles the intermediate representation of the code into the actual machine code that can be executed. Now let's go over these in a little bit more detail. So as I said, the machine arithmetic initially started to be something that give us bit vectors, so we can manipulate it. We can reason about the manipulation. So we can say, okay, if you shift something one bit left and then one bit right, you get the same thing. That sort of thing. This is really needed for verifying or reasoning about the code. But then Boris realized that this is not just enough and started building all sorts of other things around it. So now we have refinements that's essentially kind of a dependent type, and we have all the proving mechanisms based on it. But down there is still a tiny bit that is these three bindings. And if you want to play with Z3 SMT solver, and you are not really interested in refinements and whatnot, you can still use just this little bit. So that's machine arithmetic. Another bit is RISC-V. I already said that this is something that gives us a model for different architectures. We do have models of all the classic ones, like ARM, MIPS, Spark, OpenPower, RISC-V. Those last two are the ones that we use a lot, most of the time, because they are open source. I mean, even the ISA is open source and they are open source cores. So it's a nice architecture to work with because of its openness. So when you get these models or descriptions of these architectures and load them into the RC, what you get is inside the Smalltalk as a Smalltalk object the complete model of the ISA, telling you what are the instructions formats, what are the individual instructions, how they are encoded, what registers are there, how the registers are named, how big, how wide the registers are, whether it's a 32-bit or 62-bit registers. These things all belong into the model, and you can use them. You can instantiate instructions and create a ordered collection of instructions, and then that's the representation of the code and things like that. You can also get for free assembler and disassembler. The disassembler is very handy when you're actually working with the code in Smalltalk and you want to see what the code is. So you compile something, you get the bytes, and you need to see what the bytes are, what the instructions in a human readable form. You can also assemble it, so you can write just like you would write if you were writing assembly manually. You can write this and tell RISC, okay, I want the binary encoding of this instruction. And then you have a DSL, which is a little domain-specific language to actually write assembly inside Smalltalk. That's the simple way to say it. We are quite often asked whether we do support 64-bit ARM. We do, even though there are some glitches, so the support is not 100%. We have a branch for it. You can have a look. There is still some work to be done there, but for the basic simple thing, it does work. It just needs to be finished. For AMD 64, 64-bit Intel, we don't have it, not even in form of a branch. I thought about it a little bit. I think I have idea how to do it, but I haven't done it, and I'm not very sure I will have enough time to have a look at it soon. But if you're interested, just give me a shout. We can discuss. Okay, I was talking about DSL, and I just decided to give you a bit of a taste how that can be used. So if you are generating a code, for example, for RISC-V, then this is how we do it with the DSL. So you instantiate the assembler object, and then you just write branch if less than A0, that's a register 0, and if A0 is less than 0, then jump to negative. The label negative, then you do return, then you place the label, then you do some other computation and return again. So that's just a simple example of a code. But if you squint a little bit, you may say, okay, this is just assembly, right? But if you look carefully, you will see that this is also valid Smalltalk code. So you can use your standard tooling, and we use this in few experimental backends, and it proved convenient to write it this way. It's one of the things you may use. So if you get a RC, you get this model, the core stuff, and on top of that you get this DSL. You may use it, you may not use it, but it gives you the things like you can place labels, you can say, okay, I want to fix up the branch targets, so it does all the relocation for you and things. And finally, when you're done, just ask it for bytes, and that's your encoded instructions that you put in the memory and execute. Okay, let's go back to RISC-V and machine arithmetic. The RISC-V, the internal model and everything is built around the notion of the bit vector, which we take from the machine arithmetic. We use the Z3 implementation of the bit vectors, but you don't have to. If for some reason you don't want to pull the whole machine arithmetic and Z3 and other things into your image, the whole thing is engineered in a way that you can just plug in your own bit vector. There is a branch in RISC-V repository showing you how to do this if you want to. Even though I don't really see much of a reason to do it, because the bit vector in machine arithmetic works just fine, and it can do very interesting things thanks to the fact that it's all Z3 and it can solve things if you want to. Okay, the last bit is a Tinyrossa. So this is pure Smalltalk compiler. Pure Smalltalk. Written in pure Smalltalk compiler based on Tinyrossa intermediate language. That was just a decision to. I'm sorry. That was a pragmatic decision to actually don't bother ourselves with inventing an intermediate representation for a compiler, because this seems to be good enough. It's tested. People are using it. There is no problem with it. And that's why it's called Tinyrossa, because it's a tiny version of the full Tinyrossa compiler. And it's not just a JIT compiler. It's not just a AOT compiler. It's kind of both. It can depends how you configure it. So you can use it. This is a fairly new thing. I only started working on it after thinking about it for years. I started working on it this summer and haven't spent awful lot of time on it because I had other things. But it's coming out quite nicely. So maybe it's time to show you a Tinyrossa and by extension RISC-V and other stuff. So it's time for a little demo. We have to go here. So here I have Here I have prepared. Okay, here I've prepared 2 short demos showing how to use the whole thing to compile a piece of code. So first you create a compilation, which is basically the encapsulation of the whole compilation process with all the phases and everything. So you create it like this. You configure the compilation to compile for RISC-V or Linux. You can configure other things if you want to. Then you create a builder, which is again an internal DSL object builder to actually create the internal language, the intermediate representation of the code you want to compile. You tell it, okay, the function is named factorial. It returns value of type 32-bit integer. It takes one parameter or argument, which is called x, and is also of a type of 32-bit integer. And then you just build the function, right? So factorial is if x is equal to 0, then return 0, else, and so on and so forth. So you all know how to write a factorial. So once you are building, you just tell the compilation object, okay, I am done building. Now it's your job to optimize it and compile it. So if we just run it like this, let's say, I know we got halt, so that's fine. And now we can just inspect the compilation object, and we will see various things. But I actually wrote a simple tool to show you on the left side the actual compiled machine code. So this is the machine code that implements the factorial we built using the builder. And as you may see, it's not the best code ever, right? It's actually quite inefficient code. It has a lot of unnecessary stores. But that's beyond the point. The point is we have tools, and it does compile something, and this assembly is written by the RISC-V and things like this. So, and for example, if you want to see this on the left side, you have the intermediate language, the trail, which is a tree-like structure. I won't go into details because that's a big topic in itself. But for example, if you want to see, okay, for the IMOL, what instruction has been generated, you see the IMOL. For the iCall, I have these 3 instructions and things like this. So this generates the code, and then you can actually ask the compilation. Now I'm inspecting, so now I'm inspecting, but there is a method for it, and you see it can just generate the bytes, and you can even say, okay, here, so bytes, and you get a byte array with those instructions. So that's one thing you can do. I have another example, which is exactly the same like the previous example. The only difference is that I configure it to do AOT compilation. That means I tell it to save some file with the code of the factorial or any function you compile for later use, and I may then load it and preload it and so on. So this is not compiling just in time. but I do pretty much what the standard compiler does. It takes the source code, produces the compiled code, which is later on run. So I say, okay, AOT is true, I want AOT, and I want to save the object file into some file, factorial.o. So if I run this, okay, I get out. I should have the file somewhere, and if we look, we do have it here. So now what we can do with it? This file is standard ELF object file, so I can link it with another program, right? So I have written simple main, a C program, and then just calls the factorial and prints the result. So, you know, I ask it, okay, give me a factorial of some number, and it calls the function we just compiled in a Smalltalk using the Smalltalk compiler. We saved it into object file. We linked everything together. Like, you know, I'm just lazy, but that's why I have the mic. But essentially, I just call the standard JCC. You know, link it into one binary, link both C source code and the factorial we just, you know, saved into the file, and we can run it. So now you see we have the binary that is called factorial, and if I do just factorial 5s, let's say, I get 120, which should be correct. I think it is. So you see, you can create a code, link it with and call it from a standard C. I find it quite interesting, and it opens a lot of possibilities. Okay, we are running a little bit tight on a time, so let's get back to the presentation. And actually, oops, to the end of the presentation, sorry. So, to wrap up, what I wanted to say in this talk is what components we have, what they do, how you can use it, and actually encourage you to have a look, because I find it interesting. You can use machine arithmetic, or, you know, even just the Z3 bindings from machine arithmetic for your projects. You can use ArchC if you want to play with code, or you know, generate some code or analyze the code, because, for example, I use the ArchC in VDB to analyze the code, not to generate it, but to analyze, to see, you know, where are basic bugs, where are the jumps, you know, that kind of thing. Tinyrossa is a bit raw, but potentially might be interesting. So I think now it's a time for questions. I hope we will have time for questions and internet bandwidth. We'll see. But if that for whatever reason won't work, or you have questions later, here's my email. Just drop me a message if you have any questions, or, you know, want to discuss anything. I would really appreciate it.